All right. Today we'll be going over probability. Um, Probability theory is nothing but the common sense reduced to a calculation. I will say I think this is true. Probability and statistics are largely they're non-esoteric. They're very much straightforward. It makes sense. It's very logical. However, the problem is statistics without appropriate framing, without an appropriate interpretation can be misleading. Um, as well as probability. There's a reason that gambling is a multi-million, billion-dollar industry, and it constantly robs people of their money because just because it is simple does not necessarily mean that it's always our gut reaction. It's not always as intuitive as we think it is. And people have a very bad habit of misinterpreting or having a poor perspective on probability and statistics. And gambling institutions prey on that fact. They count on the fact that you do not understand probability. Okay. So while it is simple and it is common sense always it ain't always so common. This is the probability is logical, but how it plays out in real life is sometimes difficult. Um, a great example is what is the probability that you meet a mathematician? And then what is the probability that you meet a mathematician that enjoys playing poker, right? It's a very math heavy game and things of that nature. A lot of people say it's more likely you meet a mathematician that plays poker, right? Because there's numbers and calculations involved. Well, that's actually false. That's wrong. It's less likely because it belongs to a subset of mathematicians. But anyway, um, there's that. Yeah, probability and statistics are tough ones. Okay, they're simple, but require an appropriate mindset. Probability, you have the probability that coin will land heads. You have two different interpretations of probability. One is the frequentist interpretation, where probabilities represent a long run of the frequency of events. And then the Bayesian interpretation of probability, where probability is used to quantify our uncertainty about something. Hence, it's fundamentally related to information rather than repeated trials. Okay. Here we get into discrete random variables, where this is the probability of event A occurring falls in between the range of 0 to 1. Percentages are typically displayed as decimals or some ratio between the value of 0 to 1, where 0 means the event will not happen and 1 means the event will happen. The discrete random variable x, which can take on any value from a finite or countably infinite set. Okay? Think of x is simply big X, okay, is just a set of values. It's a set of possibilities. And then we have little x's. I don't like that they use x's because it's confusing, but it's just a bunch of little x's, right? And this is a countably infinite set. It goes on in perpetuity until x to the n. This could be as many possibilities as we want. Now, in the case of a coin flip, which I'll constantly allude to, there's only, guess what? There's only two possibilities. So the set of possible possible outcomes is two. That's easy. But in more complex examples, the possible outcomes are much larger. Um, but that being said, that's all this means. Of the set X, of the big X, of the set of possible outcomes, right? And for a coin example, that's heads or tails. One of those will occur. Those are the only two possible outcomes. Of the set of possible outcomes, what are the chances that it equals this unique event, little x? So in the case of heads and tails on a coin, the event one, the unique event will be heads, and the event two, the unique event will be heads, right? So the probability that out of the set that it equals this unique possibility. We could call this tails. What is the probability that a coin lands on tails? Is all this notation is saying, or just P of X for sure. Of course, we know intuitively that this is 50%, 0.5, but yeah, this is often referred to as the probability mass function or the PMF. I want to call your attention to this here. So, as we know, that big X is the set of possible outcomes. All right. Little x are the unique events or the unique outcomes. What this formula says, what this little theorem says, is this is the summation. The repeated addition of all possible events in some subset, like in some set, sorry, not subset, in some set of possible events, all the unique events add up to a total of 1. Okay? And then what that means is, I will allude back to my coin example. There are 2 outcomes. So we have two possible events that we have to add up. What are the chances that it lands on heads? Well, it's 0.5%. It's 0.5. Or not 0.5%, sorry. It's 50%, which is represented as 0.5. This is for tails. For heads, it's another 50%. We sum these up, and guess what? 0.5 plus 0.5 is equal to 1. We've accounted for all the unique events in set X, which set X is, again, the possible outcomes during a coin flip. There's 2 of them, heads or tails. We add up those 2 instances, and those equal 1. And what this 1 means, right? This 1 is, it tells us, what this theorem is saying is that out of the all possible outcomes, it is 100% guaranteed that one of these events will occur, that tails or heads will occur. There's no probability for anything else. We can extrapolate this out into maybe a die. If we're rolling a die, there would be x1, x2, x3, x4, x5, and x6 because of the 6 faces of a cube. But there would be a 100% guarantee that one of those events transpire, that something in the set occurs. That's what this means. That's what this 1 is representative of. One of these outcomes will transpire. Now there's a 1/6 chance that any unique event will occur, but I hope you're catching the change in my language, right? The unique event, there's a 1/6 chance that a specific die face will show up, but we know that a die face will show up. Okay, is the exception that's made there, or not the exception, but the rule that is being laid out in this mathematical formula. Okay, this rule also allows us to calculate. Let's say there's a cheater or a rigged coin where heads, the probability that heads occurs is 0.7. Or 70% of the time, heads pops up. This theorem, if we know the number of possible outcomes, of unique outcomes in the total set of outcomes, if we know that, we can find the possibility of other events. So, guess what? That means tails comes up 0.3 or 30% of the time. This can then be extrapolated out to dice, right? Let's say we have a dice. We have a 6-sided die, right? And there is a 50%, it's a loaded die. It's cheat dice. There's a 50% chance that a 6 will occur. And the rest of the numbers occur in a uniform distribution. They occur with equal possibility. That means out of the other 5 numbers, guess what? There's a 10% chance that a 1, 2, 3, 4, 5, or 3, 4, 5 will occur. How do I get this? It's the same thing. We know that based off this, all probabilities add up to 1, that one of these outcomes will occur. There's a 50% chance that a 6 will show up. So we do 1 minus 0.5. And that leaves us with a 50% chance, that 1, 2, 3, 4, or 5 will occur. And because I mentioned that it's uniformly distributed across the remaining die faces, we can then divide 50% by the remaining 5 unique events, right? So then this gets divided by 5, and we get 10%, a 10% chance for the rest of the numbers to occur. This formula allows us to make those assumptions and do that type of deduction. I need to cancel my drawing. Click. Okay. Again, uniform distribution. Okay. Where 1, 2, and 3, and 4 all occur at even probabilities. This is the probability that some event X is equal to the unique event of K is 1/4 because there's 4 numbers and we know all of it has to add up to 1. On the right side, we see an indicator function, okay, where this distribution represents that X is always equal to 1 and it is a constant. It's an indicator function, okay? The fundamental rules, all right? So given that the probability that 2 union events happen, the union. So the probability that A union B, well, and whenever we have a union, typically a union can be drawn as just a U, and then you have an intersection, which is drawn as like an N or an upside down U. Union means and. If you know anything about logic gates, and is that both event or English, and is that it's a conjunction. 2 things happen, 2 things occur. Given that two events, A and B, we define the probability of A or B as follows: the union, 2 things coming together. The probability that A and the probability that B occur are the sum of the likelihood or the probability of those events, only when the events are mutually exclusive. Only when the probability of A does not influence the probability of B. Okay? So if I roll a dice, there's a 1/6 chance that it lands on any unique face. If I were to roll it again, I want to determine the probability that I get 2 1s, right? I want to determine that probability. I get 2 1s in a row. The the first roll does not influence consequent rolls. It does not influence future rolls. These events are mutually exclusive. They're separate. They don't have any bearing on one another, mutually exclusive. If events depend on the probability of A occurring, if the probability that B occurs and is influenced by A, they're i.e. not mutually exclusive, then we have the probability that A occurs plus the probability of B occurring minus the probability of A intersection B. Okay. I struggle to think of an example for this right now, so we'll skip that for right now. We get into joint probabilities. We define the probability of a joint event, right? Probability that A intersection B, right? The probability, the joint probability of A and B times the probability of B. This is sometimes called the product rule. Given a joint distribution of 2 events, probability A, probability B, we define a marginal distribution as follows. The probability of A is equal to the sum of the probabilities of A and B, right? Which is equal to the sum of a probability given A. What's the probability of B occurring? We are summing over all possible states of B, of the set of B. We can define the possibility that of the set B similarly. This is sometimes called the sum rule or the rule of total probability. This product rule can be applied multiple times to yield the chain rule of probability, where we introduce MATLAB like connotation or notation. The probability that X occurs. So this is how many times in the future do I want to go? What is the probability that I roll a 1 on a dice? What is the probability that I roll a 2 on a dice given that I've rolled a 1 prior? What is the probability that I've rolled a 3 on a dice? Now I'm just going up, but this can stay a 1. What is the probability that I roll a 1 on a dice given that I've rolled a 1 and a 2 prior? Now we know because those events are mutually exclusive, the fact that you've previously rolled does not influence it. But there are events where the probability of something occurring is influenced by previous events. This is where we use this notation and the chain rule. The probability that let's get a little toxic, all right? The probability that Trump gets elected, we'll just call it right now, despite polling data, just for the purposes, probability of T for Trump is equal to 50% because there's two candidates. Because nobody's actually seriously considering RFK. And if you do, you need help. It's 50% because there's two candidates, right? The probability that he occurs. Given that he occurs, what is the probability that the economy crashes, right? So it's given. It's there's an initial probability. What is the probability that the big E, the economy, you got the econ, crashes given that Trump is president, right? So you have a probability of Trump being elected of 50%. So 0.5. And then the probability of the econ crashing, let's say that's 25%. So we have our little asterisk times 0.25. What does that give us? What's 0.25 of 50? I don't know. I can't do this math right now. What's that? You do 25, that'd be 5. Oh, it'd just be a quarter of 50. So 12.5. So it'd be 0.125, which is 12.5%. The probability of both these events occurring is 12.5%. That's the chain rule. It just says that, yeah, given this, well, what's going on? Conditional probability. We define conditional probability of event A given that B is true as follows. The probability of A and B over the probability of B, where the probability of B cannot equal 0 is greater than 0 because guess what? You can't divide by 0. Conditional, that this is the same example, but let's assume if we do the Trump example again, we assume that Trump is already president. So therefore that probability goes to like, 1 or something like that. You have Bayes' rule, combining the definition of conditional probability with the product and sum rules yields Bayes' rule, otherwise known as Bayes' theorem. The probability that some unique event small x out of the set of x occurs, and the probability that some unique event y out of the set of possible probabilities of y occurring over the probability of that unique event occurring for y is equal to this big old nasty formula here. This is the product rule, right? The little chain rule that we had up here over the sum rule, right? So then we get Bayes' theorem. An example, medical diagnosis. As an example of how to use this rule, consider the following medical diagnosis problem. Suppose you're a woman in your 40s and you decide to have a medical test for the screening of breast cancer called a mammogram. If the test is positive, what is the probability that you have cancer? This obviously depends on how reliable the test is. Suppose you're told that the test has a sensitivity of 80%, which means if you have cancer, The test will be positive 80% of the time with a 20% margin of error, where X is the probability, or where X being 1 is the event that the mammogram is positive, and Y is 1, where is the event where you have cancer. Okay, so we can actually draw a confusion matrix based off of this, right? Where we have X. Oh no, this would be X, and this would be Y up top, where we have 0 and 0 and 1 and 1, right? So this is a true negative, where you would say, I guess a true positive in this case, but either one, where the screening says where X is the mammogram is positive. So if X is 0, that means the mammogram is negative. The mammogram did not detect cancer, and Y is 0. So that means you don't have cancer. So this is a true negative. It is true that you don't have cancer. So true, no cancer. True, and I'll say no. In the event that the mammogram is positive, but Y is still 0, this is you don't have cancer, but the test told you you did. This occurs at a probability of 20%. Why? Because we know that the probability that 1 in 1 occurs that you do have cancer, excuse me, that you do have cancer, but and it detects it 80% of the time. It is in the event that you have cancer, this occurs 80% of the time. In the event that you do have cancer and it doesn't detect it, this occurs 20%. All right, and it'll reliably detect this guy 80% of the time. And of course, these would be split over this, and these would be split over this diagonal into their appropriate percentages. But that's kind of like the false positive, false negative, true positive, true negative instance that you can have. But anyway, many people conclude that they are therefore 80% likely to have cancer. But this is false. It ignores the prior probability of having breast cancer, which is fortunately quite low. The probability that you have cancer is actually 4%, 0.4%. Ignoring this prior assumption is called the base rate fallacy, and will often lead us to false detections more often than not, right? We also need to take into account the fact that the test may be a false positive or false alarm. Unfortunately, such positives are quite likely with the current screening technology, with the probability that X occurs where the mammogram comes back positive, but you don't have cancer being 1%. If I were to draw the confusion matrix more accurately, which I will do now, all right, the probability that X and Y 0, 1, 0, 1. So the way that this should be drawn is the probability. So they said the probability of it finding cancer, the probability that the mammogram machine goes off, X is equal to 1 and Y is equal to 1, is 80%. Or you could think about it like this: the chance that the machine is right is 80%. So the fact that X and Y are equal, this occurs 40%. This occurs 40%. The fact that the machine is correct occurs 40% of the time. And it has a 20% margin of error, so a false positive or a false negative. This occurs 20% of the time. So this would be 10% and 10%. The false negatives add up to that 20% margin of error, and this adds up to the full 80% of correctness. is the appropriate way. I should have drawn it the first time. But that's why it's 0.1, is because that 20% is split between two possibilities. Combining these three terms in the Bayes rule, we can compute the correct answer as follows. All right. What is the probability that you do have cancer and that the machine gives you a true value? So we know this was given to us that the machine has correctness of 80%. So 80% is denoted here times the probability or the likeliness of having cancer, which is 0.004, extremely rare, over the probability that it accurately predicts times probability of having cancer, plus, here comes the sum, plus the probability that the mammogram returns a false positive. The mammogram, when x is equal to 1, says that we do have cancer, but y is equal to 0, meaning we don't, so it's a false positive, times the probability of us not having cancer. Well, we derive this 0.996 from this 0.004. What is the probability somebody develops breast cancer? It's this 0.4%, right? There's a 99% chance that you don't have breast cancer, just like in nature without the screening. The probability that you don't have breast cancer is derived from this 0.04. So the rest of the population is this. And of course, this is given from, this is written out for, in a formula sense here. In other words, if you test positive, you only have a 3% chance of having breast cancer instead of the original 80%, which was the margin of correctness for the machine. Independence and conditional independence. We say X and Y are unconditionally independent or marginally independent, denoted by this symbol here. If we represent the joint as the product of the two marginals, it'd be given as the probability of X times the probability of Y. In general, we say a set of variables is mutually independent, mutually exclusive, if the joint can be written as the product of marginals. Unfortunately, conditional independence is rare because most variables can influence other variables. We say, therefore, X and Y are conditionally independent. Given Z, IFF, which is if and only if, the conditional joint can be written as a product of conditional marginals. We have various probability distributions. We have Bernoulli distributions. We suppose a coin toss where we let X equal the full possible set. And the set is either 0 or 1, where it's a binary variable with the probability of success, or heads. We consider heads a success and tails a failure. We say that X has a Bernoulli distribution, and it would be written as such, where the probability mass function is defined as the following. Bernoulli is the indicator function, okay, the constant of 1, the probability that the event is successful, multiplied by the probability that the event is not successful. In other words, the likelihood that the event occurs is directly, this goes back to the fact that we have two events, and we could subtract from one to find the other because they all have to add up to 1. That's all this is saying. That's all this is saying. We can derive it that way. But then we have binomial distributions, where we let X is an element of some number of n elements in that set. Where we let n be the number of heads. If the probability of heads is theta, then we say X has a binomial distribution written as the binomial of number of n elements given some theta. The probability mass function is defined as the following, where n is the number of times that we successfully flipped. Then we have the number of successes minus the number of, wait, sorry, n is the total occurrences of coin flips. K is the number of successes, or the outcome that we want to find. So in this choice, it'll be heads. Is the number of ways to choose k items from this n. This is known as the binomial coefficient and pronounced n choose k. We have Gaussian distributions, okay, or your normal distribution, joint probability distributions, covariance and correlation. Oof, this is all right. This is some intense math here. Information theory. Information theory is concerned with representing data in compact fashion as tasks known for data compression or source coding, as well with transmitting and storing it in a way that is robust to errors, a task known as error correction or channel coding. Representing data requires allocation short code words to high probable bit strings and reserving longer code words for less probable bit strings. We have entropy. The entropy of a random variable x with distribution p denoted h of x, or sometimes h of p, is a measure of uncertainty. Entropy is the measure of chaotic nature in the system or uncertainty. In particular, for a discrete variable with k states, it's defined as the summation, the negative summation of k number of states over, and it starts at state one to state big K, where the probability of some unique event K occurring is given by the logarithm of base 2 of some probability K. Oh my goodness. Yeah, that's some crazy math right there. For a special case of binary random variables where there are only two outcomes, we can rewrite where p of x, this is like the Bernoulli, where big X is equal to 1 is theta, and the other probability where x is 0 or not 1 is given by 1 minus theta. Then we have mutual information. Consider two random variables, x and y. Suppose we want to know how much knowing one variable tells us about another. We can compute the correlation coefficient, but this is defined for real valued random variables. And furthermore, this is a very limited measure of dependence. Okay, a more general approach is to determine how similar the joint distribution is to the factor distribution. This is called mutual information and is defined as the following: the summation of x and the summation of y, given the logarithm of various events occurring. So yeah, this was a rough one, man. Holy moly. Some of this math got crazy quick. And how dare Laplace say that some of this was common sense. It requires a lot of thinking, I'll say that. It does require in-depth thinking. Simple yet difficult. But thank you to Laplace for his contributions to the domain of differential equations and the mutations that we can do thanks to his Laplace transform from the continuous to the discrete time space. That being said, don't ask me any questions. Some of that got kind of hairy. Toodles.